In this example, we'll be solving a problem involving bearings. Radar stations A and B are on an east-west line 3.7 kilometers apart. Station A detects a plane at C on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. Find the distance from A to C. We'll begin with a sketch. We'll have A be here. B will be at this point. And the first thing we're told is that they are 3.7 kilometers apart. Next, we're told that Station A detects a plane at C at a bearing of 61 degrees. Now, the way we measure a bearing is from north, which is a vertical line, and we now measure 61 degrees this way. That means we would be on a line like this. So that bearing goes all the way. Now, B simultaneously detects the same plane on a bearing of 331 degrees. So again, we draw the vertical, and we measure 331 degrees this way, and then we draw a line meeting it here at point C. What we're asked to find is the length from A to C, which I'm going to label with a little b since it's opposite side B. Remember, this is 331 degrees. Well, now let's take a look. Since the way that I've drawn these is on a direct east-west line, as we were told in the problem, that means that this entire angle here is a 90-degree angle. And therefore, inside here, the angle would have to be such that it would be 90 minus 61, or in other words, 29 degrees. What about the angle inside here? Well, again, this is the east-west line, which means if we come around from here to this line, that is 270 degrees. Subtracting 331 minus 270, we find that this one is 61 degrees. Well, what's good about that is if we now add these together, 29 plus 61, that's equal to 90 degrees. That tells us that this angle, C, must be 90 degrees. We're dealing with a right triangle. Next, what we're interested in is this side B. We can find side B because in this right triangle we have the hypotenuse is 3.7 kilometers. We have this angle is 29, and that would be the side adjacent to angle 29 degrees. And so we say that the cosine of 29 degrees is equal to the side adjacent, B, divided by the hypotenuse, which is 3.7. Therefore, B will be equal to 3.7 times the cosine of 29 degrees. Substituting all of that into a calculator, we will find that B is approximately equal to 3.2 kilometers, and that's the distance from A to C. A ship leaves port and sails on a bearing of north 47 degrees east for 3.5 hours. It then turns and sails on a bearing of south 43 degrees east for 4.0 hours. If the ship's rate of speed is 22 knots, nautical miles per hour, find the distance that the ship is from the port. Well, we can begin this by first finding the distance traveled on each of the legs of this trip. Let's begin. We use the formula that distance is equal to rate times time. And let's call this part of the trip leg B. And that would be equal to the rate, which is 22 knots, times the time, which is 3.5 hours. So we would multiply 22 times 3.5, and that's equal to 77 nautical miles. If we do the same for this other leg, which I'll refer to as leg A, the rate is 22 knots times 4.0 hours, and that gives us 88 nautical miles. So now what I'd like to do is put that information onto a diagram as well as some of the information about the bearings. So let's take a look. What we have is port A, where the ship leaves and goes on a bearing of north 47 degrees east. So that would be this. Now, this we know because we've calculated it is 77 nautical miles. Now, from this point, the ship went on a bearing of south 43 degrees east. So that's represented here. And we know that that was an 88-mile trip. What I want you to notice is that this angle ACB is the sum of these two angles. Well, this angle of 47 we can get from the original bearing of 47 degrees because we have parallel lines here that are cut by a transversal, and so the alternating interior angles are equal, 47 and 47. Adding these together, we now see it creates a right angle 90 degrees. So we're now dealing with a right triangle here, where are the two legs, and this is the hypotenuse, which we've labeled as little c. We're going to use the Pythagorean theorem that tells us a squared plus b squared equals c squared. And so substituting in, we would have 88 for A. For B, we would have 77. So we would have 88 squared plus 77 squared equals c squared. Now I would add together these and take the square root of each side. That is to say that c would be equal to the square root of the sum of 88 squared plus 77 squared. Evaluating this on a calculator, c will be approximately 120 nautical miles. In this example, we'll be using trigonometry to measure a distance. A method that surveyors use to determine a small distance d between 2 points P and Q is called the subtense bar method. The subtense bar with length b is centered at Q and situated perpendicular to the line of sight between P and Q. Let's look at the figure. Here we see point P and Q. The line of sight is right here. There is the distance d, the angle theta, and then notice that if this were side B in its entirety, that each half would be B divided by 2. B divided by 2. Angle theta is measured, and then distance d can be determined using trigonometry. So let's take a look at an example. Find d when theta equals 1 degree 23 minutes 12 seconds and the length of b is equal to 2.0000 centimeters. I've recreated the picture here, and what we now are going to look at is that we have information of d and the b over 2 and the theta. What we need to use turns out to be cotangent of theta divided by 2. We're looking at then this angle here. And what we have is cotangent of theta divided by 2 is going to be this side adjacent, which is d, divided by the side opposite, which is B, divided by 2. Let's simplify that a little bit and solve for D at the same time. So we'd multiply B over 2 and find that D is equal to B over 2 times the cotangent of theta divided by 2. Let's take the information that we're given, that here's the angle theta, here's the side B, and so we know that D is going to be equal to B, which is 2, divided by 2, times the cotangent of theta, 1 degree. Of course, we want to convert this to a decimal degree. On the calculator, we can do that. What we'd find is that it's equal to 1.386667 degrees, rounding it off, and then we divide that by 2. So this would then be approximately equal to, using a calculator to do the actual calculation, 82.634110 centimeters. That would be the length of D from P to Q. Let's do another part of this particular example. Angle theta usually cannot be measured more accurately than to the nearest 1 second. How much change would there be in the value of length D if theta were measured 1 second larger? Well, that means, of course, that theta would be 1 degree, 23 minutes, 13 seconds. Converting that to the decimal degrees, it would be equal to, or approximately equal to, 1.386944 degrees. Now, we use the same formula that we just used, which is that D is equal to B, which is 2, divided by 2, times the cotangent of the angle divided by 2. So 1.386944 degrees divided by 2. The result this time would be that D is approximately equal to 82.617558. And now to find the difference, we subtract. So that difference would be equal to the value that we found first, 82.634110, minus this one, 82.617558. And that difference, when we work it out, would be 0.016552 centimeters. So that's how much of a difference there would be by increasing the angle by 1 second. In this example, we'll be solving a problem involving angle of elevation. Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet. From the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. So here's a figure that shows our tree. The first angle of elevation, 36.7 degrees, is back, quote-unquote, X, because we don't know what it is. He then moves 50 feet this direction, looks back up at the top of the tree. The angle of elevation is 22.2 degrees. I've recreated a smaller and not as illustrative scaled drawing where we have the height of the tree, H. the unknown distance where the angle of elevation is 36.7, and then 50 feet further back where the angle of elevation is 22.2 degrees. What we also know is this is a right angle, and therefore we have two right triangles. Let's first deal with the smaller triangle, that meaning this one here. And what we can say is, since we want to find h, that would be the side opposite the 36.7. The other side, we don't know what it is, but we've labeled it x, is the side adjacent. Therefore, we can use the tangent trigonometric function and say that the tangent of 36.7 degrees is equal to h divided by x. And we can solve this equation for for h, and that would be that h is equal to x times the tangent of 36.7. Let's stop there and now look at the triangle that includes the 22.2 degrees as well as that 50, and do the same process. That is, find the tangent of 22.2 degrees. That would be equal to the side opposite, h, divided by the side adjacent, which is the sum of x and 50, so x plus 50. Let's look at solving this equation for h. H would be equal to x plus 50 times the tangent of 22.2. Now let's distribute, and we have that h is equal to 50 times the tangent of 22.2 plus x times the tangent of 22.2. So now what I have are two equations, both of which have been solved for h. That h is the same h, so what we can now do is set the two equations equal to each other because they each are equal to h. Let's take a look at that. Here's my first h. H equals x times tangent 36.7. Here's my second equation for the same h. 50 tan 22.2 plus x tangent of 22.2. So therefore, I'm going to say that x times the tangent of 36.7 is equal to 50 times the tangent of 22.2 plus x times the tangent of 22.2. So we need to solve that equation for x, and I've written that on a new piece of paper because we need more space. So let's take a look. So that's the equation. We want to solve for x, and that means I will subtract x times the tangent of 22.2 from both sides. So I have x tangent 36.7 minus x tangent of 22.2, and that's equal to 50 tangent 22.2. Now what I want to do is factor out the common factor x. So I have x times the tangent of 36.7 minus the tangent of 22.2. That's equal to 50 times the tangent of 22.2. To solve for x, I now divide 50 tan 22.2 by the tangent of 36.7 minus the tangent of 22.2. So x is equal to 50 tangent 22.2 divided by tangent of 36.7 minus tangent of 22.2. At this point, I could substitute all of this into a calculator and calculate x, but because there's more to do with the calculator, let's go back to the equation which we solved in the very first part of the problem, where we had h was equal to x times the tangent of 36.7. And let's substitute the value of x that we've just calculated here to say that h would be equal to 50 times the tangent of 22.2 divided by the tangent of 36.7 minus the tangent of 22.2 times the tangent of 36.7. At this point, let me reintroduce a new piece of paper on which I've pre-written that, so that we can now say that using a calculator and substituting each of these values into that calculator, that we will find h is approximately equal to 45. And that means that the tree is approximately 45 feet tall.